Today we're going to do section 9.10, and this will conclude chapter 9, our longest chapter this semester. And kind of a culmination, what we're going to be doing today is finding general power series, Taylor series, Maclaurin series, for things that are sort of going beyond the scope of the ones we did last time. In particular, last time we worked with geometric series. We worked with some summation problems, right? But they still went back to the geometric series. We looked at integration and derivatives, but then they went back to, everything was about geometric series, right? So what if it isn't a geometric series? And that's where we're going to land today. So as a reminder, I'm actually going to write a little bit of what I just said down. Last time, we focused on using the geometric series. To find power series. We ended with using this series, that is the geometric series, along with derivatives and antiderivatives. So in this section here, we will look at a general process for finding the power series of a function. I'm going to tell you how we're going to do that. Theorem 922. If F is represented by a power series, the summation from n equals, or we'll just do summation itself because in limits of integration could change. The summation of a sub n times x minus c to the n, that's a power series. For all x in the interval I, containing c. Then, that a sub n, that coefficient, is actually the nth derivative evaluated at c divided by n factorial. And there is a proof for this in your book if you would like to take a look at it. I'm not going to focus our attention on there today, but it is proven there. And so if I combine those two statements together, and in particular what I mean is this one and this one right here, I would actually get a power series form that looks something like this. F of x equals f of c plus f prime of c, whoops, I said c and I wrote x, c times x plus f double prime of c times, I'm sorry, and I left out the x, the c minus, that's what happens when you keep moving too fast, x minus c here. Okay, f double prime of x of c times x minus c squared, and it's over 2 factorial. And it will continue. I'll just write out one more. So the third derivative at c over 3 factorial times x minus c to the third. And if you continue this process indefinitely, so to speak, you will have a power series expansion for that function. So it's all about taking derivatives and evaluating them at the c value. A little bit of notation, definitionally speaking. Not really got space here. Let me do this. Okay. If a function f has derivatives, of all orders at x equals c. So it's just saying you can continue to repeatedly take the derivative. So you guys know that polynomials don't have that feature, right? Eventually when you take the derivative, they zero out and they're done. That's not the way it works for things like sine, e to the x, 1 over x. You take their derivative and they just continue repeating forever. So that's what it's talking about for the all orders of x business. Then the summation from n equals 0 to infinity of f, the nth root of, I'm sorry, not the nth root, the nth derivative of the function evaluated at c over n factorial, which is exactly what we wrote out above. Oops, I forgot my times c, x minus c again. Times x minus c is f of c plus f prime of c times x minus c plus f double prime at c over 2 factorial, x minus c squared, and so on.
Is it supposed to be x minus c to the end?
Yes, thank you. Yep, let me fix that. It's on my paper, I just didn't get transposed, thanks. In particular, this has a name. So this is called the Taylor series for f of x centered at c. If c equals 0, what do you think it might be called? Yeah. If c equals 0, it's the Maclaurin series for f. Okay, so we're going to find some. And just a couple of guidelines on how we go about finding these Taylor series, or specifically Maclaurin series if we happen to have c equal to 0. As you're taking a look at the definition or at the theorem, either way, what you're noticing is that you're going to have to take some derivatives, right? You're also noticing that the derivatives are evaluated at a certain location, yeah? And if you'll remember from last time, just like when we were working with geometric series, there may come a point at the end where you have to clean up the notation a little bit and compact it, right? We had an example last time where I messed up my sign and it messed up, and I sent you guys a picture of with my correction actually. But it was a good example of doing just that, where I had to clean something up at the end and it ended up simplifying and there weren't all the pieces left over because they collapsed. So some guidelines for finding these, we'll write it down now. This is a Taylor or Maclaurin series. So the first issue is to differentiate f of x several times and evaluate at c. So in particular, we're going to have like f of 0, not 0, c, f of c, f prime of c, f double prime of c. That c looked like a 0. Whole bunch of them, okay? We're going to use the sequence where a sub n equals f, so the nth derivative evaluated at c over n factorial, and we'll say find the interval of convergence, if it's requested anyway. Fit the series together and simplify if possible.
Do you need the times x minus c for number 2?
That's a good question. Not for what I was describing, because I just described it as a sub n.
Okay.
So in the series over here, if you'll notice, there was a sub n right here, and the x minus c to the nth is part of it. It's just, I'm kind of lumping that into what I'm calling step 3 down here to put it together. So those are just the coefficients that we're determining in step 2. And of course, we're not going to, y'all are not at the point where I need you to label this as step 1, this is step 2. It's just to give you a sense of what comes next, right? These guidelines. All right, we're going to do one example. We're going to do an example with one function, I should say it that way. And we're going to find both a Taylor series and we're going to actually then center it at 0, which is going to make it, of course, a Maclaurin series. And then I'm going to actually show you something else kind of cool. And I don't have my book here today, but you will have yours, or at least have access to one, so I can show you what I'm referencing. So let's take a look at, an example. We're going to use the definition of Taylor series, because that's all we've talked about at this point. To find the Taylor series centered at C. And the function that we're going to do this with is e to the 2x. And our c value, as I mentioned, is going to be c equals 0. So the first thing I'm supposed to do is to take a bunch of derivatives. And so you might be looking at it and go, well, how many is a bunch? Which is a reasonable question. Yes, Ethan?
Maclaurin. Yeah, it's identified now.
Huh?
Maclaurin.
Yes, it's Maclaurin. That's right. Uh-huh. Yeah, and so we're going to find this centered at that c value, and we're going to take several derivatives. So the first one I'm just going to rewrite because I'm just going to kind of make mine in a column format. So I've got the function over here, and then I've got the evaluation for it over here. If you would like to do it in a different patterning or something like that, that's fine. But we're evaluating it at 0. So what is this function evaluated at 0? It's 1. It's e to the 0, so it's 1. What would the derivative of this be? 2e to the 2x, which would then make the derivative's evaluation at 0 what? 2. How about the function's second derivative? What is it? 4e to the 2x, exactly. So its second derivative evaluated 0 is what? 4. We're going to do one more. How about a third derivative? 8e to the 2x. And my third derivative evaluated at 0 then would be an 8. So do you notice a pattern going on with these coefficients? 1, 2, 4, 8. Yeah, it's actually got a pattern that's called geometric. It's a geometric pattern, oddly enough. That doesn't always happen. If we were evaluating this at a different point or at a different function, we potentially could get different things. But on this one, it's a geometric sequence. In particular, if I were to write these terms out, which I will in a moment, I'm going to be able to find a pattern in how they're written. And if you remember from back in the day, this is a ratio 2, right? And then it's raised to power n or n minus 1, depending on how we're starting with n. But this is basically 2 to the n, right? Okay, cool. So we're going to then establish that we have each of these coefficients for the values x minus c, but c is 0, so x, and then divided by the factorials as we go down. So it looks something like this. So we've got the sum from n equals 0 to infinity of the first coefficient, 1, as a constant. The second coefficient is 2 times x minus c, but that's just x because our c value is 0. And it's divided by 1 factorial, but that's just 1, so this is just 2x. Everybody good with that? The next one is supposed to be 4. It will be times x squared, and it will be divided by 2 factorial. So you'll notice that the power here and the factorial down here match, right? That's going to keep happening. Let's write one more out since we did it a third derivative here. I would have 8x cubed over 3 factorial, and then of course it doesn't end, so let's make sure we notate that properly. Okay, so I shouldn't have written this yet, I'm sorry. I want this part, but I want it down here to consolidate the moment later. It's okay, just erase it. Yeah, this is f of x is what I meant to write here. I was just preempting what I did. I want the summation. Okay, so this is actually what it is written out. I need to consolidate it to write it into a series notation instead of this expansion of the terms. All right, so let's take a look at what we have in terms of powers. Well, you know that you have x to the n, right? And we know that the denominator is in factorial. That's not changing. And then the first part of what we're looking at is going to be this sequence that I got up here. And then I need to make sure that my n actually works, and it's not supposed to be n plus 1 or n minus 1 or something like that, right? So is it 2 to the n? If I put 2 to the n in here, do I get what I want? Or do I need to shift that n? It's right, isn't it? Yeah, it is. And we can leave it written like this. If it bothers you that you have 2 to the n, x to the n, you could combine them so it says 2x, all of it to the n. That would be another possibility. So you could do, let me use a different color. You could write it as a summation from n equals 0 to infinity of 2x to the n over n factorial. It's a little bit more compact. It's not that bit different, so either way is fine. Way to write that. This one doesn't ask for an interval of convergence, so we don't need to find it. Some of yours will and some of them won't. Most of them I don't think in this lesson do, actually. So. All right, does anybody have their book with you, or can you grab it or look on with a neighbor real quick? Grab your book. I would like to not actually show the book on the screen because then I have to stop the recording. And we have several people who are catching up on this from at a distance. The point. Oh, what page do you need to look at? I need you to look at page 670. Okay, there's this like giant chart on page 670. Does everybody see that? Or if you're nearby somebody else, would you look on their book just so that you can see the chart? So in this chart, what you see is you see some power series expansions for some specific functions, like you see sine, you see e to the x, we see arctangent of x, we see a few of the rational expressions. Look, there's that 1 over 1 plus x that we did last time that was geometric. So we've got some basic functions right here. Okay, so keep your book open to this because I want to show you how you can use this table, and you will have this table on your test to use when it's appropriate to use it. I'm not going to make you memorize the table. That seems like a waste of your brain, don't you think? It does to me. So you'll have this table, and let me show you how you can use this table with the same example we just did. So we just did the example for e to the 2x, right? And let me give you directions before I get going too far. So here are directions for this particular problem. Use the table of power series. It's on page 670. To find the following power series. There. Okay, and we're doing the same function that we just did, and basically I'm showing you how we could use that table and end up with the same result. So two different ways of doing the same problem, basically. Okay, so from the table, it tells you what e to the x is. Written out, it actually tells you that it's 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on. Just as a general rule of thumb, I tend to stop at 3s because I feel like that I see enough of it without it becoming too long, but if I stop at 2, sometimes I don't see the whole expansion of how it's really looking, so that's where I tend to stop in mine. Okay, so if you're using this, what you can actually do is a simple substitution. So if I'm going to be finding, in this problem, e to the 2x, I can simply replace every x with 2x, right? So if I do that carefully, I will have a 2x here. I will have a 2x quantity squared here, a 2x quantity cubed here, and I'll have my dot, dot, dot there at the end. And if you take a look back at the series that we got, I've got it on another screen over here, it's exactly what it is if we were to multiply out the powers of 2. In particular, it's almost friendlier that it's written this way, because you can actually see that you've got the summation from n equals 0 to infinity. It's the power 2x, or sorry, it's the coefficient 2, not coefficient, but it's the term 2x that's being raised to the power of n, and I'm dividing it by the n factorial. And again, if you wanted, you could write it as 2 to the n x to the n. That'll be fine too. But it's the same thing, same expansion. So two different ways of doing the problem, and sometimes in math people get a little freaked out about that. The directions tell you, right? They tell you which way to do it. Think back to when you learned derivatives for the very first time, and the first way that you did them was a really long method, right? Limits. Remember that? Limit as h goes to 0 of f of x plus h minus f of x over h. Shake your head if you remember doing that. David's not sure. It's okay, David, I'm sure you did. I don't know where you took your calculus, but I'm sure you did it. It is a long process, and then shortly after that, and usually after you've taken some sort of a quiz or a test over it, somebody says, but there's these wonderful shortcut rules, and you're going to love them. And then after that, everybody's like, do I have to do it the other way too? And usually the answer is, only if I ask you to, right? Same thing here, okay? So you have two different ways to do the problems. If you're looking at a particular problem on this homework assignment, just make sure that you're following the directions that they're giving you. Sound good? Okay, so I have your homework assignment. And what I'd like for you to do, this is page 673, before you leave, is to find one of them that you have to find by hand, just to make sure that you guys are sort of tracking with me on the process here. 27, 30, 33, and 36. And just in case any of you are like super diligent, I mean, I know it's a Friday, but I know also that some of you guys are like super diligent. WebAssign is not up yet, but it will be within the next hour, okay? So don't go look at there and think she's just not going to assign one. I am. I just didn't get it pulled up into there yet. So I'm giving a test here in an hour and, in the next hour. So it'll be up soon, okay?